All right, hi everyone, welcome to our presentation. Today we are going to be talking about how to tackle the global plastic pollution problem through our plant design for the production of polybutylene succinate, which is a bio-based biodegradable plastic. We are BU Sucks. I'm Emma Viveiros.
I'm Jankowski.
I'm Rudy.
And I'm Rachna Igwa.
So to talk a little bit of background on the plastic pollution problem, since plastic has started to be produced in the 1950s, over 8 billion tons of plastic have been produced. Roughly half of this is for single-use disposables, so plastic cups, plastic silverware, packaging, etc. Only 9% of all plastic produced has ever been recycled, which leaves a huge surplus that is polluting our environment. This surplus ends up in landfills and in the ocean and is causing a huge problem. It causes danger to humans and to animals because it leaks toxins and carbon dioxide into soil, water, and the environment. So far, over 1,200 marine species are endangered due to plastic pollution. Additionally, traditional plastic is produced from oil, which is a non-renewable resource. So in whole, this is not sustainable and is causing huge devastation to our planet. To start off, our group tackled this problem by creating a Kepner-Trigo analysis of all of the ways that this problem can be tackled. This includes reducing the use of plastic or using plastic alternatives, cleaning up plastic that's currently in the ocean to be recycled into new products, or creating alternatives to plastic such as bioplastics. The term bioplastics covers both biodegradable plastic, compostable plastic, and bio-based plastic. The difference between biodegradable plastic and compostable plastic is that compostable plastic can only degrade in a compost setting, which is a very specific environment, while biodegradable plastic can degrade in both compost settings, landfills, and the ocean. To have a holistic solution, we decided to approach biodegradable plastic and try to create bio-based plastic as well so that we are not using a non-renewable resource. So across the world and the US, some of these approaches are already in place. As we've seen in Boston and other places in the US, there's legislation to reduce the use of plastic bags. Consumers are also turning towards alternatives to plastic disposables such as paper straws. And in places around the world such as India and especially Europe, there is new legislation to completely ban the use of traditional plastic for single-use disposables. So this is something that factored hugely into our approach, especially in our market analysis, and we'll delve into that soon. And this also brought us to the conclusion that the best solution for our group to approach was to create a plant that produces bio-based and biodegradable plastic.
So having settled on bioplastics as our primary focus, we wanted to narrow down into one specific product that we would be generating. And so we were considering all of these as options: polyhydroxybutyrate, polycaprolactone, polyethylene, and polybutylene succinate, which are very similar in structure, and polylactic acid were all of the options that we considered. We ruled these out for a variety of reasons. Polyhydroxybutyrate we thought would not be degrading as easily in landfill and ocean environments, which is very important to us. In addition, polycaprolactone we thought might have problems kind of on the opposite end of the spectrum, where it would degrade a little bit too easily and wouldn't hold up to the applications that we were planning on using it for, which made it not an ideal alternative. PLA, polylactic acid, is already being commercially produced, and there has been some success with it, but we were hoping to introduce a new product to the market to diversify a little bit, and we also think that polyethylene and polybutylene succinate could be used for a broader range of applications, so that kind of steered us away from PLA. And between PBS and PES, we discovered that PBS has a little bit more workability, and it's easier to mold into a variety of different shapes for different applications, so we thought that we would be able to generate a wider range of products using that plastic. So a little bit about PBS specifically. It's a bio-based, biodegradable polyester. It can easily be broken down in a compost or landfill environment, and if left in the ocean, it will also decompose and eventually disintegrate into monomers over a period of about 3 or 4 years. It's also very workable, and we would be able to combine it with a plastic starch to increase that workability or tune it a little bit more for a variety of different applications, which we thought would allow us to create a range of products just from this same plastic molecule. So to go into our plant design a little bit, we have two reactions that we would be running. One is a two-step reaction to create butanediol from a feed of succinic acid, which would be coming from a bio-based source. And those two materials, succinic acid and the 1,4-butanediol, are the two chemicals that we need in order to create the monomer for our final polybutylene succinate product. So for our plant overview, we would be starting with biosuccinic acid, which we obtain from a company that creates that product via fermentation of sugarcane. That would be fed into a hydrogenation reactor, where we would be able to generate our butanediol product, which we can separate out through distillation. And then we would combine that butanediol with some of the initial biosuccinic acid within our polymerization unit to create our PBS product, which we would then filter out and combine with our rice husk flour as a starch additive in our pelletizer. That unit would extrude the plastic, mix it together with the starch, and create a uniform finished product that would be chopped up into pellets that can then be remolded by plastic distribution companies into whatever products that they desire to make out of it.
So as Joe said, we have a two-step process. This P&ID features the first reaction, which is the production of 1,4-butanediol. We take our feed of biosuccinic acid and feed it to our hydrogenation reactor. This reactor features a recycle loop to maximize conversion. The product is then fed to our separations unit, where we have our tetrahydrofuran waste and then our product of 1,4-butanediol, which is in storage. And to highlight our hydrogenation reactor a little bit, so this reactor has a volume of 26 meters cubed. The batch time is 20 hours. In order to control the level in the reactor, we have a control system that includes the recycle feed valve and the product release valve. That's valve 3 and valve 6. We also have a pressure control system. This reaction occurs at a high pressure of 1200 psi, so we want to maintain that pressure, and then also have safety measures such as the pressure relief valve on top of the reactor. The reaction occurs at a temperature of 160 degrees Celsius. So to maintain that, we also have a temperature control system, which controls the flow of cooling water to the jacket of the reactor. The next step is the creation of polybutylene succinate. So we take our 1,4-butanediol product and mix that with more of the biosuccinic acid. This mixture is then fed to our polymerization reactor, where it is ramped up to the temperature of 270 degrees Celsius for the polymerization to occur. Once again, we do have a recycle loop to make sure that we're maximizing our conversion. Once the polymerization is complete, we then take our product and, as Joe said, feed it to our mixing and pelletizing station. This is where the addition of rice flour will occur at different proportions depending on what our consumer has requested, and then the pellets will then be distributed to our consumer. So to highlight our polymerization reactor, this reactor has a volume of 20 meters cubed and a slightly shorter batch time of 12 hours. Once again, we do have a level control system that includes the product release valve and the recycle feed valve. The reaction for this one occurs at atmospheric pressure, but we do still have a pressure relief valve in place for safety. We also have a jacket on this reactor that has a thermal fluid instead of water to maintain the reaction temperature of 270 degrees Celsius once it's ramped up. And just like the first one, this is connected to a temperature controller linked to the inside of the reactor.
So next we went and did a proof of concept analysis, and so this is our Aspen model basically. This would be the first reactor here, B1, and B2 would be the second reactor. For the creation of BEO, we found that there was a batch time of about 20 hours with a total conversion of about 80% in each step of the reaction. And for PBS, we found a batch time of 12 hours with also a conversion of about 80%. And these were both found in papers in the literature. So then what we had issues with was actually simulating the polymer aspect of this, we were able to simulate the actual formation of BDO, but the formation of the PBS was very difficult due to the fact that PBS is a newer plastic and the fact that polymers are really difficult to simulate in Aspen. So for the BDO process, we started with this one and we did it in Aspen. Instead of doing it in just one reactor, which is what we would actually do in reality, we split it into 2 reactors. So this would just be the biosuccinic acid going into B1, and then coming out over here would actually, which is S4, it would actually be the BDO. And so what would happen would be the biosuccinic acid would go into B1, it would go in with methanol, and then it would come out as dimethylsuccinate, and it would go in with hydrogen gas. And so in B2, it would have a reaction there, and then BDO would come out. And so in the end, we'd get 1,4-butanediol, and that would be the product flow rate of about 138,000 kilograms per batch. So then we looked at the material balances. Due to the fact we had a really difficult time modeling the PBS in Aspen, we did a material balance in order to figure out what the initial masses of everything all our precursors would be needed. And so we started with the second unit, and that would be the polymerization step, and we would want to make about 3,000 metric tons of PBS per year. And so after calculating about 300 working days and then about 2 days per batch, we calculated about 15,000 kilograms per day. And from there, with 80% conversion, we were able to calculate how much butanediol would be needed, and that would be about 10,000 kilograms per batch. From there, we went to the desired output of 10,000 kilograms per batch with a 64% conversion due to the 80% conversion on the first step of the butanediol reaction and 80% conversion on the second step of the reaction. And we were able to get those values over there as the kilograms needed for the precursors.
So now we'll talk a little bit about the plant safety and health considerations. Here's a safety data sheet with all of the materials and properties of these materials. And as you can see, one of the bigger hazards is the flammability and health hazard on the NFPA diamond rating. This means that we will need proper handling, safeguards, and PPE to be heavily enforced to make sure that safety is paramount in our plant. So some of the main process safety concerns would be overpressurization and flammability. To combat overpressurization, we have pressure relief valves. We also have an agitator in R201, and that's to prevent any polymer buildup during the reaction. We also want to implement inherently safer design, especially on the hydrogenation side. So that includes a separate SIS for that hydrogenation reactor, as well as proper design specifications for all of the equipment, pipings, and fittings for hydrogen use. We also want to have an outdoor facility to make sure that we have proper ventilation to prevent any hydrogen pockets. Same for flammability, we also want that proper ventilation. That will be helped with the outdoor facility, educated operators and clear instruction, relief valves and explosion-proof materials, as well as an automated control and alarm system to only allow safe controls. So now we'll go a little bit into the economics. Here's a graph that shows the global plastics market. As you can see, in 2013, bioplastics held less than 1% of the global plastics market, but projected to grow into 40% of the market share by 2030. We've identified some key factors for that. There are many more bioplastics coming into the market as of recent years, and more formulations and testings to make sure that they can be feasible replacements for traditional plastics. So this is contributing to that growth. As well, there's more awareness about the detriments of plastic pollution, and there are legislation and regulations that are hindering plastic manufacturers from using these traditional plastics. One of these that's helping our market is the EU plastic strategies. They're trying to cut plastics waste, especially targeting the top 10 most common single-use plastic products, as you can see to the side there. We believe PBS, especially with the flexibility of the starch additive, is a really good replacement for these types of products. So the main initiative is to ban these single-use plastics in the traditional plastic use, and that constitutes for over 70% of all marine litter. They also have more sustainable measures such as labeling requirements, increasing consumer awareness, and incentives to plastic manufacturers to use more sustainable replacements. So here's current PBS production worldwide. As you can see, all our competition is in Asia right now. So besides just the market, we want to get into that European area to be the only competitor. We want to produce 3.6 kilotons per year, so we are on track with our competition.
And then the other table is the suppliers of bio-based succinate acid, which is the precursor we do have to purchase, and we are going with Viveiros. So Viveiros is an Italian source of biosuccinic acid, and it's made from fermenting sugarcane. This is also a benefit to us because the prices of biosuccinic acid tend to be lower, especially because it's more stable than the volatile market of oil prices. And it's also beneficial for our plant location, which is Saarbrücken, Germany. And that's chosen for the national tax laws, EU regulations, and Saarbrücken is a good location for the nearby river and port network. It's also close to our supplier, Viveiros. So then we went into capital costs. Here is analysis of the capital costs. We basically looked at the major equipment costs, which include the 7,000 gallon high pressure reactor, the 5,000 gallon polymerization reactor, the distillation column, a separator, and some packaging machine costs. And we combined those together to get the total equipment cost at the top there, which is around $3 million. And then from there, we were able to calculate the ISBO, the OSBO, design and engineering, and the contingency. And combining that all together, we got a total capital cost of $65 million. From there, we went on to look at the cost of production, and this would be the variable cost of production. And these would include all our raw materials, plus utilities, effluent, and distribution. And so with the total raw materials cost, we got around $4.7 million per year. And then with our total value variable cost of production, we got about $5 million per year. So then we looked at fixed costs. And so we were able to create a pie diagram of how the fixed costs would be distributed. But we started with operating labor, supervision, direct salary overhead, maintenance, rent of land, insurance, and sales team. And these are all super important parts of actually creating a fixed cost for the year. For operating labor, we would have a 3-shift schedule. And for the sales team, we would have 3 locations with 2 salespeople each. And so in total, we got around $500,000 per year. So then we looked at the economic projections of our plant. And so with the total capital cost as $65 million, total cost of production around $5.5 million, and the total revenue around $19.8 million per year, we had a net margin of $19.2 million per year. And so this was assuming that the cost we would price the PBS around $6.60 per kilogram. And so here you can see our net present value of cash flow. And you can see around year 7 is when we would break even. And so this is a very conservative estimate. We are assuming that it's only we're only selling 3,000 tons a year. Every year for 10 years, but in reality the demand of the plastic would most likely go up, as well as the price of biosuccinic acid becoming a more better and rigorous process would actually go down. So in reality, we would probably break even before year 7.
So as far as applications, we found that we would be able to tune the applications of our product by adding different amounts of that rice husk flour starch when we polymerize the product. So for finer applications like thin films, plastic bags, and fishing nets, which can make up to 40% of marine litter in the ocean, these would require a higher starch loading because they need to be a little bit more delicately produced and extruded into thinner sheets. But for larger products with a more solid structure, food containers, plastic silverware, medical devices, and that type of application, we would be able to use less starch in those as they don't need to be extruded in such fine and specifically defined shapes. So in conclusion, we've determined that polybutylene succinate is a bio-based and biodegradable alternative that can be very effective in helping to reduce some single-use plastic waste. We've also found that adding starch can increase the workability and degradability of our plastic and give us a wider range of variety in our final products that we make from our plastic. And so with an initial investment of about $65 million, we would be able to create a plant that can generate profits within 7 years, and thus PBS is the ideal alternative to traditional plastics that are currently used for single-use products.
Thank you.
Thank you.
Any questions?
Any questions?
So you mentioned that PLA is already on the market, and I was wondering if you could directly compare your solution to the PLA that's already out there. So why is yours better?
Yeah, so we found that PBS is a little bit more workable than PLA is, and it would also be more conducive to starch loading in the polymerization step. And we thought that that would be a way for us to generate more product on less expensive scale, since some of the volume of our final product would be taken up by that flour instead. And that would also give us more options to create for a final product, since the plastic would be more, the workability would be more adjustable. Anyone else?
What waste considerations do you have to worry about in your effluent?
I think we would have to go back. Do you mean the tetrahydrofuran waste, or
Just in general, yeah. So what, if you're having these reactions, what do you think you have to be concerned about in terms of disposal?
Yeah, so we do have the tetrahydrofuran waste, which we would need to work with a contractor of waste disposal for that. We also have the effluent, so the gas and hydrogen being released. I think that we would consider adding in a flare for some of these gases so that they're not directly released to the environment.
And I know that some of the waste would be held in outdoor storage tanks, and then we would contract out waste disposal teams to take care of that. But we put money in the budget and the capital cost, or in the variable cost budget for effluent matter, so we'll have a way of disposing and money that would go towards it.
I have a couple. What's the mode of degradation for PBS?
So it depends on the environment that it's in. So for example, if it's kept in water, it slowly is decomposed back into monomers, so the succinic acid and the butanediol. As far as within a compost environment, it's broken down by bacteria, and having that rice husk flour sort of biomatter inside as well helps to kind of create pockets where it'll break down more easily. So it slowly degrades into smaller and smaller pieces, and then, you know, on large time scale of a year or two, depending on the product that's being used. So for example, a thin film would degrade more quickly than a more solid piece, but that's, the bacteria generally breaks those down. And then within a landfill, it's just more like physical degradation of the polymer, like breaking back into smaller and smaller pieces. And again, those are in turn disposed of.
And we did actually see in the literature that it decomposes into water, and some sources said that it decomposes into a small amount of carbon dioxide, and some said, I think depending on like how much starch you add, there can be some like monomers, as Joe said, but the majority breaks down into water and carbon dioxide.
So if it's undergoing hydrolysis, do you think you have to worry about the local environment becoming too acidic?
I don't think so. So the succinic acid is already made by a lot of, for example, small organic molecule or small molecules or single-celled organisms and that kind of thing make succinic acid as a byproduct of some of their biological processes, and it probably wouldn't contribute unless a massive amount of polybutylene succinate was being dumped inside a very small water source, for example, which we don't think would be the case. If anything, it would be disposed of in the ocean, so it wouldn't affect the acidic content of the water source that it's placed in. Yeah.
But that's also absolutely something that in scale up we could have an environmental contractor help us to do some studies just to make sure that that's not something that will greatly affect our community.
Is it a thermoplastic polymer?
It is a thermoplastic, that's correct.
Do you know where the glass transition phase is?
The glass transition occurs at, I believe it's about 250 Celsius, but it's slightly above the temperature that it would be exiting the reactor.
So one of the potential advantages of this over current market is that it's stable at higher temperatures. So I can stir my coffee without it.
Right, exactly, yeah. Even though it does degrade in like water, or especially heated water, for example, you wouldn't have to worry about your spoon melting. Yeah.
And a big part of this is that it's single use, so like you wouldn't be using that coffee stirrer over and over again. It'd be like you use it and throw it away. So it'd be like in businesses or like in a cafeteria where you're just using the spoon once and then throwing it away. So there'd be like no chance of that basically.
Yeah, that is something that we considered instead of
Yeah.
aiming for like long-term like plastic water bottles. That is something that we would have to, you know, run studies with like FDA, like if it leaches into the bottle, which is why we wanted to focus on just, you know, one-time use disposable.
Especially because it's such a big part of plastics pollution.
But if it, so earlier you said it did last like 3 to like up to a few years to degrade.
Mhm.
So
So
that
that's
could
within
be-
a
In the
water
ocean, yeah.
environment, yeah.
Right, but if you're making a water bottle, that's I mean, that could be beneficial potentially.
No, it
It
would
could be applicable, but like you said, with the hydrolysis creating too acidic of an environment, we would want to run studies before we used it for something, for
case it
example, a
leaches
water
into the
bottle,
water,
since it's so
yeah.
enclosed, yeah. we
So our
wanna
plan
make
was
sure
mostly just
it's
to
safe.
use it for like silverware, like maybe cups, like things that you would, not a water bottle basically.
But there is potential for that type of application, we would just need to be doing more research into that.
So some people have allergies to like rice flour and things like that. If you're adding that in, do you think that would be a concern?
I think that would just come down to consumer awareness and labeling. That would definitely be a top priority for us to make sure that we address all those concerns and, you know, put that front and center on our labeling.
And other starches can be used. We just chose rice husk flour because it is a promising starch for us, but really based on the consumer and what they're looking for their application, we could use different starches in different amounts.
I sort of have a question on the economics of it. So you did all your calculations out, which I think were really thorough. Do you think that 7 years is a reasonable time frame if you're building up and trying to get consumers buy-in?
I think a huge part of it that probably wasn't stressed enough is going to be like the sales team making sure they do diligent work. I mean, targeting the European market is like a huge part of like what our team wants to do in order to make sure that we find a market that, and it's definitely a niche market since they actually are going to have laws and like policies banning this plastic. And so basically like it'll come down to our sales team like creating connections maybe with the government, different factions of it, and figuring out a way of like getting our company to be known. I think a big part of like selling that much plastic will be like having our company known as like maybe one of the top providers of plastic in the area. But 7 years is like probably a little short of a time frame. You'd have to think about a lot of the aspects of like getting your name out. But I think like seeing that our numbers are already like really, really conservative with the fact that we decided to keep like a steady amount of revenue each year, I think 7 years could be like a very reasonable number as long as we put in a lot of money into the marketing and sales at the very beginning.
Furthermore, a lot of worldwide companies are making pledges to be traditional plastic free and move to sustainable options. So if we could get a contract with even one of those companies, I think that would greatly help our projections.
All right, just a quick question on your reactor since you have it there. Is there any concerns for fouling? Or you said this is a continuous process, but is there any times you have to shut down?
So it is actually a batch process. I think, yeah, we might not have stressed that enough. And we do have time included in the economic projections of the amount of like batches per year. There is time in between, and that will be used for reactor cleaning and safety checks to make sure that there's no concerns about the thickness, especially for our hydrogenation reactor, which is at a very high pressure.
Any questions from everybody else? Okay, I think I got my questions, so. All right, with that, thank you guys.
Thank you very much.
Thank you.